Good morning, students. Today we will discuss axiom spaces, which are also called first countable space and second countable space. So first of all, we define what is first axiom space or first countable space. So let us take a topological space X top. This space is said to be first countable space if for every x belonging to this space X there exists a countable base for the neighborhood system of this point X. So if we have a countable base for the neighborhood system of every point of X, then we say that the space is first countable space. Let us see some examples of first countable spaces. First example is indiscrete topological space. In the indiscrete topological space, the topology tau1 that consists of the sets phi and the set X. Now let us take an element X belonging to X. Then, because the only open set containing this X is the whole space X, and therefore we can say that in discrete topology the neighborhood system of X that consists of the whole space X. Now let us take beta X. This is a collection consisting of the set X. Then clearly we can see from here that this beta X that is a sub collection of nx, and also this is countable collection. So beta X forms a countable base for the neighborhood system of the point X, and therefore in discrete topological space is a first countable space. Now let us see another example, which is discrete topological space. Discrete topology is denoted by tau2, which is a collection of all the subsets of X. Now let us take an element X belonging to X, and beta X is the collection of all the singletons. Then this beta X that is a base for the neighborhood system of this element X. In order to show that this is base for the neighborhood system of X, let us take W be a neighborhood of X. Now because W is neighborhood of X, so X belongs to W, and from here we can say that singleton X that is contained in W, and also this singleton X belongs to this collection. It means singleton X belongs to beta X. Thus we can say that for W belonging to neighborhood system of X, there exists a member from base collection beta X such that X belongs to existing member that is contained in the given neighborhood. So by definition we can say that this collection beta X that is base for the neighborhood system of the point X, and also this collection that is countable collection. So there exists a countable base for the neighborhood system of the point X, and therefore we can say that the space is first axiom space. Now next, there is important property of these spaces, hereditary property. What is hereditary property? This is a topological property of a topological space. We say that the property is hereditary if every subspace of the topological space also has the same property. Then we say that the property is hereditary property. Now we prove that the property of first axiom space of countability is hereditary property. It means we have to prove that subspace of first axiom space is first axiom. So let us take a first axiom space X top, and let us take Y with the topology tau y, which is called subspace topology. So we have taken this be a subspace of the topological space X tau. Now we have to prove that this space is first axiom space. It means we have to show that for every point belonging to this space there exists a countable base for the neighborhood system of that point. So let us take an arbitrary point y belonging to this subspace y. Now because y is contained in X, so this y is an element of X. Now because X is first countable space, so by definition they will exist a countable base, say beta y, for the tau neighborhood system of this y. Now yesterday we discussed the lemma. If we have base for the tau neighborhood system, then we can form a base for tau y neighborhood system. So let us define the collection beta star y, which is formed by the intersections of y with the members of tau neighborhood system's base beta y. So we have taken the members A from beta y. Beta y is base for tau neighborhood system of y. So in this way we have formed beta star y. Now by previous lemma, this collection is a base for tau y neighborhood system of the point y, and also this collection is countable because beta y is countable collection. So we have obtained a countable base for tau y neighborhood system of the point y, and by definition if we have a countable base for the neighborhood system of the point, the space becomes first axiom. So we have proved hereditary property for first axiom spaces. Now next we define what is second axiom space. A topological space X tau is said to be second axiom space if there exists a countable base for the topology tau. Let us discuss an example of second axiom space, the usual topological space, that is second axiom. We show that the space is second axiom. So let us take a collection beta of the open intervals whose points A and B are rational numbers. Now we show that this collection is a countable base for the topology U. In order to show that this is base, let us take a member A from usual topology. So by definition of usual topology, we can take A of the form of open interval Hk, where H and K are real numbers. Now let us take X belongs to A. It means X belongs to the open interval Hk. Now between two real numbers there lies infinitely many rationals as well as irrationals. So we can find two rational numbers A0 and B0 lying between H and K such that H is less than A0, less than X, less than B0 and less than K. Thus we have obtained X belonging to the open interval A0, B0, and this open interval that is contained in Hk, and this interval that is denoted by A. Thus for A belonging to U with X belonging to A, there exists this member from the base which is contained in A, and by definition we can say that the usual topological space is second axiom space. Now next, there is important theorem. Every second countable space is first countable, or we can say that every second axiom space is first axiom. So let us take a second axiom space X tau. We have to prove that it is first axiom also. So by definition, because X is second axiom space, so there exists a countable base, say beta, for the topology tau. Now we have to form a countable base for the neighborhood system of every point of X. So let us take an arbitrary point x belonging to x, and let us form a collection consisting of those members of beta which contains x. Now we claim that this collection is a countable base for the neighborhood system of the point x. Now let us take WB a tau neighborhood of the point x. We can apply the definition of neighborhood. By definition of neighborhood, there exists a member from tau such that x belongs to that member G that is contained in the given neighborhood. So from here, x belongs to G is contained in W. Now because G belongs to tau and x belongs to G and beta is base for topology, so by definition of base for G belonging to tau with x belonging to G, there exists a member A from beta such that x belongs to existing member that is contained in G. Now because G is contained in W, so from here we have x belongs to A is contained in W. Thus we have proved that beta x is base for neighborhood system of the point x, and also this is countable. Therefore we have obtained a countable base for the neighborhood system of the point x, and so we can say that the space is first axiom. Now next, the hereditary property of second axiom spaces. Means we prove that the subspace of second axiom space is second axiom. So let us take x tau be second axiom space and y with the subspace topology tau y, this be the subspace of the space x tau. We prove that this subspace is second axiom. Now because the given topological space x tau is second axiom space, so by definition there exists a countable base for its topology. Let us take beta be that countable base for the topology. Now let us define a collection beta star by taking the intersections of members of beta with y. Now we claim that this collection is a base for the topology tau y. So let us take a member B from this relative topology with x belonging to B. Now because B belongs to relative topology, so by definition of relative topology, the members of relative topology are formed by taking the intersections of y with some members of tau. That member we have taken as G. So B can be written as G intersection y. Now because x belongs to G, it means x belongs to this intersection. So by definition of intersection, x belongs to G as well as x belongs to y. Now x belongs to G and G belongs to tau, and beta is base for the topology. So by definition of base, there will exist A belonging to beta such that x belongs to A is contained in G. From here A intersection y is contained in G intersection y, and G intersection y, that is B. So we have obtained x belongs to A intersection y, that is contained in B. Now by definition of this collection beta star, we can say that A intersection y belongs to beta star. Thus we have corresponding to B belonging to the topology tau y with x belonging to B, there exists a member from beta star such that x belongs to existing member that is contained in B. So by definition beta star is base for the topology tau y, and also beta is countable, so beta star will also be countable. Thus we have obtained a countable base for the topology tau y, and therefore the space y tau y is second axiom space. Now the last topic is separable topological space. A topological space is said to be separable if it has countable dense subset. For example, we take usual topological space, and we already discussed that the set of rational numbers that is dense in set of real numbers. So Q is dense in R, or we can say that the closure of set of rational numbers is equal to set of real numbers, and also set of rational numbers is countable. So we can say that the usual topological space that is separable. Now next there is a theorem: every second countable space is separable. So let us take a second countable space, X top. Now by definition of second countable space, there exists a countable base for the topology. So let us take beta is countable base for the topology tau. And because this is countable, so we can take beta of the form of the collection of members a n, where n belongs to set of natural numbers. Now we can use axiom of choice. So according to that, we can construct a new set A by taking exactly one element from each an. So let us take A is formed by taking the elements an, where an belongs to these an for every natural number n. Now we will show that this A is dense in X. Now we have already discussed the characterization of dense set. A set is dense if and only if it intersects every non-empty open set. So let us take a non-empty open set G. We are to show that A intersection G is non-empty. Now G is non-empty, so we can take an element X belonging to G. Now because X belongs to G and G belongs to topology, and beta is base for topology, so by definition of base, for G belonging to tau with X belonging to G, there exists some member H from beta such that X belongs to H, H is contained in G, and therefore from here we can say that A intersection H is non-empty, implies that A intersection G is non-empty because H is contained in G. So we can say that A intersects every non-empty open set, and therefore the set A is dense in the topological space X tau, and also A is countable. So we have obtained a countable dense set, and therefore by definition the topological space X tau is separable. यार
कोणती ऍक्टिव्हिटी
दोन